University of Southern Carolina, who is going to talk to us about homological mirror symmetry for Batyrev mirror pairs. So please welcome.
Okay, thank you everyone, and thanks very much for the invitation to be here. Sorry I couldn't be there in person. I hope it's been a wonderful ICBS so far this year. The title of my talk is Homological Mirror Symmetry, or HMS, for Batyrev mirror pairs. And in this talk, I'll be describing joint work with a collaborative team of Hanlon, Hicks, Pomerliano, and Sheridan. Primarily, I'll be following this archive paper 2406.05272, but I'll draw on earlier paper of ours as well. And I'm using a laser pointer to select things. I hope people can see if I write something like this. Can people see the test? Okay,
we
great.
Can see
Thumbs
that, yes.
up. Wonderful. Okay. So I'm going to start this talk by describing the result and the setup of the result, and then I'll spend some time talking about the proof of this result and what's new in our argument, as opposed to, compared to existing methods to prove homological mirror symmetry, cases of homological mirror symmetry. Okay, so the statement of the result requires us to recall a recipe for producing mirror pairs that goes back to the early days of mirror symmetry. Okay, and I'll describe the recipe in broad brushstrokes. I won't go into all of the details, but it's a combinatorial recipe that produces mirror pairs, proposed mirror pairs of Calabi-Yau hypersurfaces and toric varieties. The starting point is we start with a Y star, a projective phonotoric variety. Projective phonotoric varieties are described by a certain class of polytopes combinatorially, these reflexive polytopes. And there's a purely combinatorial operation called polar duality of reflexive polytopes that produces from Y star a new polytope and therefore a new toric variety called Y bar. It's the polar dual toric variety. It's phonotoric as well. However, it's typically quite singular. So we don't work with Y bar. We resolve it to something I'll call Y. It's actually only a partial resolution in general. It's still projective phonotoric, but it's more smoothed out. And that resolution depends on one additional auxiliary choice, which is a vector of real numbers, kappa sub p. P lies in an index set, which is controlled by some combinatorial data from the underlying toric variety we began with, namely some subcollection of lattice points, okay, associated to the polytope. So we start from Y star, we produce Y bar, and then from Y bar, given an additional vector, some data, some extra input data, that vector needs to be generic. It needs to lie outside of some walls. We produce a Y. This isn't the mirror construction yet. We now pass to hypersurfaces on both sides. So within Y star, we pass to a family of hypersurfaces, which I'll call XT star. Okay? XT star is a family of Calabi-Yau hypersurfaces where T is an element of some affine space AP, given by observing that the sections of the anti-canonical on Y star are have a natural basis coming from certain lattice points of the polytope, and we look at some sums of formal combinations of such sections, and we get some large family of hypersurfaces, XT star. So this will be our B model, or our complex geometry side of mirror symmetry. And on the A model, or symplectic side, we begin with Y, and we pass to a single Calabi-Yau hypersurface, a smooth one, if possible, equipped with a Kähler form called omega kappa, coming from the ambient toric variety. Namely, omega kappa should be a Kähler form that is Poincare dual to the sum of kappa p times the Poincare duals of dxp, where here dyp are the toric divisor strata of Y, and then we just intersect them with X to get intersected toric strata in X, and we take a Poincare dual of a combination of them, depending again on the same kappa generic vector. That was part of our data in constructing Y. Okay, so we get here a hypersurface, which is a fixed hypersurface. However, there's a Kähler form that depends on this parameter kappa. So the proposal, which goes back to Batyrev's seminal 1993 paper, is that the X star on the B model side or complex geometry side, and the X on the A model or symplectic geometry side should be mirror pairs. And it was observed, even going back to that paper, that they satisfy the requisite exchange of Hodge numbers. Subsequently, we learned that they have, that there's enumerative mirror symmetry for them from work of Geventhal and Lian-Yu Yao. However, we had not known homological mirror symmetry for a large class of these. And so my main result is going to describe a homological mirror symmetry statement for a wide class of these. So before I make the statement, we'll make further assumptions in order to state our theorem. We'll assume, in the original construction, the projective phonotoric we could have started with could have been an orbifold, but we'll assume it's smooth. We'll make an additional assumption. We'll assume our complex dimension of our ambient toric variety is sufficiently large, greater than or equal to 3 for simplicity, and we'll also assume the X we get from the construction, this Calabi-Yau hypersurface right here, is smooth. This can occur even if Y, the partial resolution, wasn't completely smooth, provided we can find a hypersurface that misses the singular points. Okay, so I have to make one more recollection before I state a result. So let me recall the following construction of a field from your favorite choice of ground field K. There's an associated Novikov field, which I'll call lambda or lambda sub K with K, or lambda with lambda implicit, with K implicit rather. And this Novikov field is the sum of it's a set of formal countable sums of the form sum of AI to the lambda I, where AI, the coefficient, lies in the field K we started with, and lambda I are real exponents, and the only restriction on them is they must tend to infinity in this set. So the theorem, joint with Henlin, Hicks, Parmeliano, and Sheridan, is under these hypotheses stated above. For each kappa, this vector of real numbers that's generically chosen as above, there exists a B of kappa, a lambda point in affine space, and an equivalence of DG or A infinity categories over lambda between something I'll explain in more detail here on the left, but some sort of Fukaya category, and some sort of, on the right, the DG category of bounded coherent complexes on X star sub B of kappa. So X star sub B of kappa is the restriction of this bigger family to this lambda point B of kappa. This lambda point describes sort of some embedding of spec of the Novikov field inside affine space. So let me explain what I mean on the left-hand side to make this equivalence precise. So when I say the symbol Fuk of X omega kappa, I mean some version of the Fukaya category of the compact Calabi-Yau hypersurface. I will specifically, for the purpose of this talk, use a model of the Fukaya category called the relative Fukaya category of the pair XD. X has this natural divisor D here. Let me just make sure I write that. So dx is the union of all the restrictions of toric strata. And this model of the Fukaya category was studied considerably in work of Seidel, Sheridan, and Sheridan. Just in broad brushstrokes, I'm not going to give formal definitions of this talk. I want to treat it more as a conceptual entity. But roughly speaking, this category is built out of certain compact Lagrangian submanifolds plus extra data. The morphisms are lambda vector spaces freely generated by intersection points if the pair of Lagrangians we're taking morphisms intersect transversely. And there are differentials and compositions which count certain J holomorphic disks. And we count J holomorphic disks of a particular symplectic area with a coefficient weight T to the beta. This is where the Novikov field starts appearing in these counts. And then we sum over all possible areas, and in general, there may be an infinite sum, because there may be infinitely many disks if we allow arbitrary areas, but there are only finitely many below any given fixed area. Now, there's one issue in this definition, which is that we say, well, there's a differential that implies that actually the morphism should be a chain complex, but in general, that's not the case. What one gets in general is what's called a curved A infinity category, And there's a curvature term a priori coming from counts of J holomorphic disks with one output. It prevents the differential from squaring to zero and leads to curved versions of the A-infinity equations. So there was a superscript here called BC, and that's designed to extract from this curved A-infinity category a genuine A-infinity category. It's the process of passing to the A-infinity category of objects equipped with bounding cochains. Okay, so the end result of taking the category of bounding cochains, objects with bounding cochains in this curved A-infinity category is a genuine A-infinity category. Or maybe uncurved A-infinity category. There was an extra decoration called perf in front, which indicates perfect modules. This is the idempotent completed pre-triangulated hull of an A-infinity category. This is a correction that has to do with the fact that on the right-hand side, the category we're considering is idempotent complete and pre-triangulated, whereas the Fukai category, upper BC, may not be, so we need to close it up. We need to make it a little bit larger in order to have a comparison to the other side. In this theorem, we say that for each kappa, there exists some B of kappa, some mapping from the Novikov field into affine space. So one can ask, what do we know about the map kappa to B of kappa? And a priori, we know nothing other than the map must exist. So it's a priori unknown from our theorem what the map is. We just know it exists using methods of deformation theory. We call this map kappa to B of kappa the mirror map for homological mirror symmetry. However, a posteriori, using work of mine with Peretz and Sheridan plus structural properties of Fukai categories in preparation, we can show that B agrees with the usual mirror map coming from enumerative mirror symmetry, which is characterized in terms of certain Hodge theoretic considerations. So a priori, we don't know what it is, but using compatibilities of this map with enumerative mirror symmetry or Hodge theoretic mirror symmetry, we can actually pin down what the map is. Another comment on the result is our paper constructs, what it does is it constructs an embedding from the right-hand side to the left-hand side. And this embedding split generates by an automatic split generation result of myself and Sanda, which in turn appeals to structural properties of Fukai categories, which in this context of Fukai category still works in preparation. So that's one caveat. And the two more comments about the statement of the result before I move on to describe how we prove the result. So one is that this holds in characteristic 0, so not k equals 0, but for characteristic k equals 0. So we started with some Brown field and then took the Novikov field over k. So you can ask what k is this valid for? And the statement is valid in characteristic 0, so for a characteristic 0 field, but also it's valid in positive characteristic, provided we exclude finitely many positive characteristics. Okay, and which characteristics to exclude depend a bit on the combinatorics of our starting problem. So depending on the polytopes we are using in our Batyrev mirror construction, there are a certain collection of bad characteristics one can extract from the combinatorics, and as long as we're not in a bad characteristic, we can work with a field of a non-bad characteristic. In particular, the Fukai category in this context can be defined over these finite characteristic Novikov fields. This was already demonstrated in work of Peretz Sheridan in this context. So maybe the last comment about, and this is the comment I'll spend the most time elaborating on over the course of this talk, the proof of this mirror symmetry theorem, homological mirror symmetry theorem, invokes structure theory for Fukai categories. It invokes topology and combinatorics. It invokes some geometric arguments. The geometric arguments we use are mostly not new. They go back to work of Abu Zaid on homological mirror symmetry for toric varieties. However, we do not use any direct enumeration of holomorphic disks in this argument. So that's maybe one thing that's new compared to other works on homological mirror symmetry for compact calabi-Yau's. So maybe I'll pause for a second and ask if there are any questions about the statement of the theorem, and then I'll spend some time describing the proof and our approach.
Yeah, it seems that I actually have a question because I don't understand what is the significance of this vector of Novikov coefficients of B of k.
Yes. So the idea somehow is this Novikov field is some sort of one parameter. You know, it's sort of some one parametric version. I mean, if we allowed only integer exponents, it would be something like the functions on a formal disk, right? So we should imagine it's like functions on a formal disk. However, good.
Yes. What is B of k? What is so you have on the right hand side you have coherent category, derived category of
Yes.
x star B of k.
Yes, so what I'm doing is I'm restricting. So I have x star. X star is a family over AP, and I have
yes.
spec lambda in here, and I'm restricting.
And it's a fiber, yes.
Yeah, exactly.
Okay, thank you very much.
Mm-hmm. Thanks for the question. Okay, so let me spend some time talking about the proof strategy, and what I want to do in this discussion is I want to talk about what the basic strategy is for computing, in particular compact Fukai categories, which appear on the left-hand side of this homological mirror symmetry statement. And there's a basic strategy for computing these Fukai categories, which goes back to a proposal of Seidel in 2002. But then I also want to describe what's new about our approach from there. So Seidel's proposal is, if we want to compute the Fukai category of X, we should first try to begin by studying what's called a large volume limit, or LVL of X. Namely, that's X minus D for D an ample divisor. And this X minus D will be equipped with some infinite volume symplectic form, which is obtained by sending this divisor to infinity. So I'm just going to ignore this text for now, and I'll just focus on a picture. Okay, so the picture of such an X, a model X, is on the left-hand side here. So here's an X, a particular hypersurface in projective space, and here's a particular D, and if we pass the large volume limit, we send these 3 points on the torus to infinity, we get some sort of punctured, thrice punctured torus with cylindrical ends heading to infinity, which has infinite volume. Okay, and there's a mirror procedure in nice cases, which is called the large complex structure limit. So this procedure can often be compared on the mirror side to a large complex structure limit of the mirror. So let's recall the mirror of this symplectic picture. So here's the A model, here's the B model. The mirror is some sort of family of Calabi-Yau hypersurfaces over something like a punctured disk. So a large complex structure limit is a particular degeneration of that to a more singular variety over a central fiber. Okay, so we extend this family to a disk instead of a punctured disk, and then we restrict to the special fiber. Okay, so and we'll call this large complex structure limit X naught star. Okay, and we'll call the large volume limit X minus D. Okay, so here's let me write something. Here's this large volume limit. Here's this large complex structure limit. And we expect that we can find a large complex structure limit associated to our large volume limit that matches up with it via the mirror construction. I'll explain why this is helpful in a minute, but in our example, there's a natural candidate of D. Maybe I should just say, in our case, the D we're going to use is this toric divisor, meaning the intersection of the toric divisor with the hypersurface. Okay. Okay. So that's what we'll use for our D. And then we can ask what's the corresponding large complex structure limit on the other side. Okay. So remember, xt was a family of Calabi-Yau hypersurfaces in our toric variety y star, xt star. So here, a natural degenerate zero locus of this sort of anticanonical line bundle is the toric divisor itself. Okay. So we'll use the toric divisor of y star. And in this example, the toric divisor of y star, y is a projective space, it's a P2, and the toric divisor is a union of 3 lines meeting along 3 points like this, a cycle of 3 P1s. Okay, so why are we degenerating to this large volume limit, respectively large complex structure limit? So first of all, the idea is that we should be able to compare categories here, and it should be easier to do. So step one is we try to compare, make some sort of homological mirror symmetry statement here, which is easier, and I'll explain why. So here we expect that the Fukaya category of the large volume limit should match with the category of perfect complexes, which is complexes of vector bundles on the large complex structure limit. Now I need to be a little bit careful because this is a singular variety. So there are actually 2 interesting categories here. There's perfect complexes and there's coherent complexes, and they're different. Okay. So this is what we expect by homological mirror symmetry, and why is this a useful thing to try to study? Well, the reason is that this large volume limit x minus d is a complex affine variety, and it is in particular what's called a Weinstein manifold. In particular, it's an exact symplectic manifold. So for it to be exact symplectic, it follows, roughly speaking, the heuristic is that large disks should be absent, at least for a large class of Lagranges, these exact Lagranges. This means, for instance, that all of our disk counts aren't infinite counts anymore. We don't need to weight them by some series parameter in T. We can just perform a finitary count for any given disk problem we're trying to solve. And the expectation from this is we should be able to compute this Fukaya category, or at least portions of it, rather explicitly. So that's the first thing to say, is that this seems like potentially a more tractable statement. But then secondly, and this all goes back to, again, Seidel's observations. So far, I'm just recapping Seidel's proposal. In favorable cases, the Fukaya category of the compact symplectic manifold that we're interested in should be a deformation of the Fukaya category of its large volume limit. This was proposed by Seidel and explored considerably by Seidel and Sheridan in works on homological mirror symmetry. Concretely, just what you should imagine is this idea that if you have a Lagrangian submanifold in x minus d, but you're counting disks in the compact symplectic manifold x, well, they're weighted by some t to the area parameter, but the area parameter is roughly, up to some fixed correction, the intersection number of your disk with d. And if the intersection number is 0, we can arrange that these are just disks in x minus d. Okay? So this is saying that this t series, after some rough change, has the property that if I set t equals 0, I get disk counts in x minus d, and that's what this deformation idea is coming from. Okay, so this gives us some roadmap for what we should do, and the traditional approach to going from here relies on specific geometry and algebra computations. And these were used to spectacular effect in work of Seidel, Sheridan, and Sheridan-Smith. The idea in this traditional approach to computing for compact Fukaya categories is to start by finding a collection of Lagrangian submanifolds in the Fukaya category of the large volume limit and explicitly compute their Fukaya category up to equivalence. Then next, one should study deformations of A. Using the idea that the Fukaya category of the compactification is a deformation, one should just study abstractly what are all deformations of this collection of Lagrangians, of the category. Deformations are classified by a certain group called Hochschild cohomology of this subcategory, and in favorable cases, this group can be computed rather explicitly. And then some additional geometric and algebraic arguments can be used to constrain and then finally pin down up to equivalence all deformations up to leading order. So this allows one to say that in some cases, for certain subcategories, if I have a deformation of it and the leading order, the coefficient of t in that deformation has a certain profile, then any deformation with that property is equivalent to any other up to some change of coordinates. This is where these mirror maps come in. So then one needs to further compute the leading order deformations. There's some computation done of disks in the compactification. Finally, this one needs to argue something about this collection split generating the total compact Fukai category. So that's the traditional approach. There is still a decent amount of specific geometry and hard geometry and algebra computations going into this traditional approach. And so instead, our work takes a somewhat different tack, although it still reduces to the large volume limit and studies the deformation problem. The idea is to use functoriality topology and combinatorics. Namely, since the large volume limit is Weinstein, there's a toolkit developed by myself with Pardon and Shenda, which gives a functorial, topological, and sheaf theoretic and/or combinatorial tools for computing, well, the Fukai category, but not quite the Fukai category of x minus d consisting of compact Lagrangians, rather an enlargement of it called the RAP Fukai category. Okay, so we want to use this toolkit and try to plug it in to the deformation problem. Okay. And also, we want to study the Hochschild cohomology, which is an important invariant to compute to study deformations. Instead of using algebraic computations, we want to study it via some sort of topological methods. Okay. So, okay, this toolkit gives us a lot of tools. However, it's not computing exactly what we want. It's computing something a little bit larger. So let me try to explain how it's larger. I'm not going to give full details on what this RAP Fukai category is, but I can at least try to convince you by picture that it's something a little bit different and a bit larger than what we were actually hoping to get. So in this Fukai category of the large volume limit, we were studying compact Lagrangian submanifolds. So for instance, these blue circles in the thrice punctured torus are examples of compact Lagrangian submanifolds. Here's another one. Okay. In this wrapped Fukai category, W of x minus d, we're adding additional objects which are potentially allowed to be non-compact. They can be non-compact, properly embedded cylindrical at infinity. Okay. And there's some procedure for allowing objects like this and how to define morphisms as well. Okay. So we're getting something a little larger. Nevertheless, let's understand what we can get from that. So we can use the functoriality and topological and sheaf theoretic toolkit to establish the following result. And this was done by Gamage and Shenda using techniques from my work with Pardon and Shenda, our third paper, and work of Kuwagaki. So here's a statement of result about homological mirror symmetry for the large volume limit. So the statement is, for x and dx as above, namely x is the Calabi-Yau hypersurface, in this toric y, and dx is the toric divisor intersect with the hypersurface. So for that pair, and remember x naught star is the toric divisor in y star, the original toric variety we started with. So for this pair, there's a commutative diagram of equivalences. So one learns homological mirror symmetry statement between the large volume limit, the RAP Fukai category of the large volume limit x minus dx. It matches up with coherent complexes. Implicitly, the notation I used at the beginning had a dB dg in front, but I'm omitting that in this diagram. So it matches up with coherent complexes on the large complex structure limit, but in a way that's compatible with pushing forward to the ambient torque variety. Namely, the large complex structure limit has an inclusion. It includes, it's a sub-variety of the ambient torque variety, and the ambient torque variety itself matches a certain Fukai category. It matches the RAP Fukai category of C star to the n+1 with some data determined by a function called the Hori-Vafa potential. So this is a Landau-Ginzburg model, and I won't go into full details, but Landau-Ginzburg models have well-defined Fukai categories and or wrapped or partially wrapped Fukai categories. And this was known to match coherent complexes on the ambient torque variety, and the theorem is that the homological mirror symmetry equivalence between the large volume limit and large complex structure limit is compatible with certain inclusion functors. Okay, so let's go back to what we actually want. So what this theorem above in particular is giving us is it's comparing the RAP Fukai category, this enlargement of the compact Fukai category of the large volume limit, to coherent complexes on X naught star. What we want is some sort of correspondence involving compact Lagrangians, this Fukai category of X minus D, the smaller category. And we expect it's going to match up with this subcategory called the subcategory of perfect complexes. So this is complexes of vector bundles. Remember that for a singular variety, perfect complexes are a subcategory of coherent complexes. Okay, so this is up here is the desired statement, and down here is what we have. Okay, so problem one is to go from the desired statement to go from what we have to the desired statement. So we want to characterize, we have an equivalence between co of the large complex structure limit and the RAP Fukai category of X minus D, and within there are two subcategories we'd like to match up. And we don't need to match up the whole category, at least it's sufficient to match up sufficiently many objects which split generate on both sides. Okay, and the idea to do that is we're going to somehow try to do that by studying this diagram in much more detail, plus using some additional geometry of functoriality and or adjoints. Okay. So I'll say more in a moment, but before I do, I want to talk about the second problem. So once we've done that, then we'll have characterized a subcategory, the Fukai category of compact Lagrangians in the large volume limit, and that's a category which we hope would deform well to the Fukai category of the compactification. So we should now study the deformation problem, and pin down the deformation from the Fukai category of the large volume limit to the Fukai category of the compactification, and on the other side, from perfect complexes of the singular fiber to perfect complexes of the family of hypersurfaces. And the rough slogan idea here that we're going to use is instead of specific complicated algebra, which appeared in the computation of Hochschild cohomology. Remember, Hochschild cohomology is this is essentially the tangent, the tangent space of the deformation space. So it's sort of the first step in studying deformation problems. And we'll use some geometric or topological arguments to compute this instead of specific complicated algebra. Okay, so those are the slogan arguments, and what I want to do in the remaining time is give a little bit more detail into what's going in under the hood in these steps. I'll just pause for a second and see if there are any questions in what's happening so far.
It seems that no one has any questions, so
okay,
you may continue.
Great. So let's go into more detail into this first problem. So problem one was this problem of going from an equivalence between co of x naught star and the wrapped Fukaya category to an equivalence between perf of x naught star and the compact Fukaya category for the large volume. Okay, at least on sufficiently many objects. Okay, and the idea again was to study this commutative diagram of homological mirror symmetry equivalences somehow. Okay, and here's the idea in more details. So the observation is that let's study this push forward functor. Okay, so we have x naught star including into y star, and we have this I lower shriek functor. And the observation is that I lower shriek, which is a functor from coherent sheaves on this torque divisor to coherent sheaves on the torque variety, has a right adjoint, okay, called I upper star. And by the way, coherent complexes on the torque variety equal perfect complexes on the torque variety because the torque variety is smooth, even though the torque divisor was not. So it has a right adjoint from perfect complexes or equals coherent complexes on the torque variety to coherent complexes on the torque divisor. Okay, and it's I upper star, and one can calculate that the essential image actually lies in and split generates the subcategory we're really interested in. We were really interested in perfect complexes on this singular torque divisor, and we can characterize those perfect complexes as we take the image of I upper star, and then we look at the smallest item potent complete pre-triangulated category containing that image. For instance, and the reason, the way to see this is just to calculate that, well, perfect complexes on x naught star is split generated by these, twists of the ample bundle O of I, and O of I is the upper star restriction of O of I. Okay. So that's a quick way to see why this is true. So what we'll do is, so we'll go back to this picture and we'll see that we had I lower star, and here we have I upper star, and I upper star sends, lands in perfect complexes. So perfect complexes is the thing that's supposed to match the compact Fukaya category. So what we'll try to do is try to study the a similar adjoint on the other side of mirror symmetry and see what happens with it. Okay, so we will indeed study the mirror of this. And before I say what the mirror of this is, I want to recall work of Abu Zaid going back to coming from Abu Zaid's thesis in homological mirror symmetry and follow-up work of Hanlon Hicks. This work produces a collection of Lagrangian submanifolds in C star to the n plus 1 with boundary a Lagrangian sphere. So the Lagrangians are called Li, and the boundary of each of these Li's is a Lagrangian sphere boundary of Li lying in the fiber of this function W HV at a sufficiently far out point, which I'll call infinity. This fiber of WHV is the large volume limit x minus t. Okay, it has that property, and these Lagrangian submanifolds, after pushing them off in a certain way in infinity, they give objects of this wrapped Fukaya category that's supposed to be mirror to coherent complexes on the ambient toric variety. And these Li give objects that specifically match the twists of an ample bundle O of I. Okay. So what we'll do is we will construct a right adjoint to the inclusion functor from the wrap category of the large volume limit to the wrap category which is mirror to the ambient torque variety category. Okay, we'll construct this right adjoint called cap. The original functor was called cup, and we'll construct this functor called cap. Okay, and it'll have the property that for this Li lying in this collection of Lagrangians, the cap image of it can be geometrically computed to be this boundary of Li, which is a compact sphere. Okay, a sphere in particular compact. Okay. Okay, so what would we learn if that were the case? Okay, so if that were the case, we would learn that, let's trace through this diagram. So work of Abuzaid, Hanlon, Hicks says that these Li match up with the objects Oi. Okay? By direct computation, I upper star, which is characterized as the right adjoint of I lower shriek, sends ovi to ovi. Okay? And these ovi split generate perfect complexes on X naught star. Okay? On the other hand, the Li mapped by the right adjoint of this cup to the boundary of Li. Okay? And since there's a commutative diagram with involving cup and I lower shriek, there's also a commutative diagram involving the right adjoints. Okay? So what we learn is that under this equivalence, these compact Lagrangian submanifolds boundary of Li match up with the twists O of I. Okay? And because the twists O of I split generate all the proper objects, so perfect complexes are all the proper objects in the sense of having finite x with any other object. Since they split generate all such proper objects in the coherent complex category, we can transfer that statement across mirror symmetry to say that these Lagrangian submanifolds split generate all proper objects in the Raphkahi category. In particular, every compact Lagrangian is such an object, so they split generate the compact Lagrangian category. And they allow us to deduce the desired correspondence between perfect complexes on this large complex structure limit x naught star and the Fukaya category of x minus d, at least after taking the idempotent pre-triangulated hull perf. Okay. So that is roughly our approach to problem 1. Now I'll talk a little bit about what we have to say about problem 2. So remember that problem 2 was this question about now that we've studied we understand the Fukaya category of compact Lagrangians in the large volume limit, how do we deform it? And in particular, pin down the deformation from this large volume limit category to the Fukaya category of the compactification, and respectively pin down the deformation on the other side enough to show that the two deformations coincide up to change of coordinates. Okay? That would imply our homological mirror symmetry statement, which we desire. Okay? So the idea here is we want to use some sort of topology at infinity instead of specific complicated algebra to compute Hochschild cohomology. And let me explain what I mean by that. So we begin with an observation. The observation is on the B model side, on the algebra geometric side, we want to deform perfect complexes on x naught star. Okay? And its deformation theory is controlled by Hochschild cohomology of perfect complexes. However, there was this larger category coherent complexes floating around, and one might ask, well, if I just knew that category or just knew its Hochschild cohomology, would it be enough? And the observation is that actually the Hochschild cohomologies are isomorphic. There's a natural map there's a natural restriction map on Hochschild cohomologies going this way, because perfect complexes are a subcategory of coherent complexes, but it usually need not be an isomorphism. In this case, it is. And this has to do with the fact that our x naught star is a proper singular variety. Okay, so it's known that for proper singular varieties, there's a sort of Morita or Kojal duality between coherent complexes and perfect complexes. Okay, meaning, roughly speaking, this means I'll explain. That it means that perfect complexes on x naught star can be computed as functors from coherent complexes on x naught star to perfect K modules, where K is the ground field. And vice versa. Okay? So you could think of this functor category as some sort of categorical dual or Morita dual. Okay? And the statement is somehow that perfect complexes of X naught star is Morita dual to coherent complexes and vice versa. And this only holds if X naught star is itself proper or compact. Okay? So for a singular variety that's non-compact, this statement will fail and usually fail badly. Okay, but in this case, it's true. So we can transfer this observation to the other side of mirror symmetry and observe that this will tell us that the Hochschild cohomology of the Fukaya category of compact Lagrangians, in this case, of the large volume limit, coincides with the Hochschild cohomology of the wrapped Fukaya category. Okay? These are the two categories that match co and perf on the mirror. Right? So we obtain identical statements. So why is this useful? In turn, let me just write this. In turn, the Hochschild cohomology of the Raptokai category. So now this has become the thing we want to compute. It can be computed as follows. So there are two theorems that I want to cite that give us, in combination, give us strong control over the Hochschild cohomology. So the first is a theorem of mine using work of Chantrain, Dimitroglu, Rizal, Gijini, Golovko as work of mine with Pardon Shende and also work of Gao. This first theorem says that the Hochschild cohomology of the Rapp-Fukaya category of X minus D can be computed directly via geometric cohomology group associated to X minus D called symplectic cohomology. Okay? Symplectic cohomology is a theory, a Floer type theory for X minus D that's been studied for these class of exact symplectic manifolds for quite some time. It's a Hamiltonian Floer homology, so it's really built out of the symplectic geometry of X minus D. Its definition still uses some complicated analysis. One needs to count certain cylinders solving Floer's equation, which is a generalization of the Cauchy-Riemann equation. So it is an object of symplectic geometry. However, its definition does still involve analysis in PDE. And by the way, we are not interested in just the Hochschild cohomology. We also want to understand what is the leading order deformation class associated to compactifying X minus D to X. And this is also something we can compute geometrically in SH of X minus D coming from the so-called Borman-Sheridan elements. There's a geometric construction given an inclusion of X minus D into its compactification X of an element which is the leading order deformation of the symplectic cohomology, in symplectic cohomology that corresponds to this leading order deformation. Okay, so this is statement one. We've reduced this Hochschild cohomology computation, this algebraic computation, to some sort of symplectic geometry and Floer theory of the total space. And observation theorem two is a result of mine with Palmer-Liano, which reduces this in favorable cases to topology, completely to topology, algebraic topology, in fact. And in this case, this case turns out to be a favorable case. So the statement is that we can compute the symplectic cohomology of X minus D and this Borman-Sheridan element topologically, or at least via a spectral sequence. So there's a spectral sequence computing this group and the element inside it, which is built out of algebraic topology associated to XD. Specifically, it's built out of the cohomology of X minus D, and then it's built out of, what one does is one takes the strata of XD. XD is a stratified space coming from X minus D, and then the top dimensional strata of the divisor, then the higher intersections, and so on and so forth. For each stratum, there's a punctured normal bundle. Okay, and we look at the cohomologies of punctured normal bundles over open strata. Okay, so for instance, e.g., if D had just had two components, D1 union D2, we define D1 circle to be D1 minus D1 intersect D2. So it's the part of D1 that lies away from D2, and then we'd want something like SD1 circle, which is the unit circle bundle. C star maybe C star normal bundle. Works fine. To D1 circle in X. Okay? So these are the types of normal bundles whose cohomologies we need to compute, but this is an algebraic topology problem. So the statement is that if you've computed all these cohomologies, then you've computed the first page of a spectral sequence converging to symplectic cohomology, which is what we were trying to compute. And in some cases, the spectral sequence collapses. So even though there was theoretically some analytic counts of cylinders that were involved in the differentials for the spectral sequence, one can argue collapse in a variety of cases. And it turns out in this case, for this class of XD, one can directly analyze and prove collapse of the spectral sequence. So the computation reduces to pure topology. Okay, so putting these two together, along with the observation that the Hochschild cohomology of the Rapp-Fukaya category agrees with the compact Fukaya category, what we learn is by staring at strata of our pair X and the restriction of the torque divisor inside it, we can quickly use algebraic topology of that pair to compute the Hochschild cohomology of the Fukaya category. Okay, so now we've computed the Hochschild cohomology, but that's not the full deformation problem. That just gives us the tangent space to the deformation space. And we need to use that computation of Hochschild cohomology to learn something. So I just have a few final remarks about that. We need to argue from this computation, and there's a corresponding computation on the algebra geometric side, that the deformation problem is uniquely determined by the data of this leading order term on both sides. In particular, we need to pin down this deformation. Okay, and I'll just say a few high-level words about this. The idea of how to do this is we want to characterize the deformation by observing that on both sides there's a unique larger multi-parameter deformation, which is versal or universal in some sense. Okay, and the multi-parameter deformation on the algebra geometric side is, instead of just looking at a one-dimensional family of xt over this over this Novikov field, we'll look at the whole family of xt star for t varying in this large affine space. So this is a much larger family, and this family satisfies a certain uniqueness property in the sense that it's the unique multi-parameter family with certain homogeneity and or extra grading properties, and whatever deformation we're actually trying to compute is a specialization of that. Okay, so where's this homogeneity coming from? It's coming from the fact here we're going to use some extra input from the toric geometry of the situation. So on the algebra geometric side, there's this large torus acting on the toric variety, and that torus acts on the family. That torus doesn't preserve fibers, okay, but we can study the weights of the action on various fibers, and we still can think of our large collection as having some sort of homogeneity property with respect to this action. On the symplectic side, the extra homogeneity and or grading structure is coming from extra gradings in the first homology of the large volume limit. So those gradings give the Fukaya category of the large volume limit extra gradings, and in fact those extra gradings can be extended in some way to the Fukaya category of the compactification, in the sense that we think what we do is we study the deformation problem, but we study it in a slightly different way. We think of the deformation problem as a graded multi-parameter deformation where we weight different toric components of our divisor we're compactifying by, different components by different variable powers. Okay, so we weight intersection number by different powers, and each of our by different variables, and each of those variables has some degree which corresponds to these grading classes. So if we study this larger deformation family where we allow ourselves to partially compactify by different divisors in our normal crossings dx, we obtain this higher dimensional family of Fukaya categories, and it turns out that that satisfies a certain universality property, which we can then specialize to the one parameter families we're really interested in. Okay, so now these can be compared, and that basically is the roadmap for how we prove things. So I think that's all I have to say. Maybe let me stop there and thank everyone very much, and see if there are any further questions.
Hey. Yeah, thank you very much. So, yeah, does anyone have any questions?
Hi, Professor. I actually have two questions. Thank you for
Sure.
your talk first. So actually, could you say again about your X star 0? Because I'm thinking
Yes,
about, so it is inside Y, which is Y is a toric variety, right?
that's right. So X star 0 is inside. Let's go back to the very beginning here. So Y star is our projective finite toric variety. And inside Y star is XT star, but there's also X0. So X0, oh, sorry, I'm using something invisible. Let me try here. So inside Y star is X0 star, okay, which is just the toric divisor. Okay?
I see.
So we sometimes call that dy star. Okay, so the toric divisor is a normal crossings divisor. I just think of that as a singular variety in its own right.
Sure. So you mentioned I'm actually what I actually want to ask is
Sure.
why it is not a final hypersurface of why it cannot be a final hypersurface of Y star. Like you said, family of Calabi-Yau hypersurface, right? So
Yes.
can your theory borrow to, let's say, do something to final hypersurface?
Yes, I mean, I think I believe there's a version of this result for final hypersurfaces. And the roadmap for how one might study them, you could see in Sheridan's papers. So Sheridan has,
Yeah.
a
Yes.
paper on final hypersurface in projective space. So I think you could study the final hypersurface case, but then laying out what specifically the mirror is involves additional notation, and we also have not done all the computations in that case. I do believe it's possible, though.
I see. I see. Thanks. And actually, my second question is, I believe at the pretty much this beginning, you mentioned about the characteristic non-zero characteristic of a field.
Yes.
So, but I didn't see in the later part of your talk. But I may wonder what is that characteristic case?
The finite characteristic case, yeah. So what is the punchline here? So the point somehow is that um, if you look at this mirror construction, it works just fine in the finite characteristic case. However, what you'll see is that the family on the B model side may fail to be a smooth family in some bad characteristics because certain defining equations might vanish, and we might get something singular in finite characteristics. And roughly speaking, the combinatorial conditions we put, and I didn't specify exactly what they are, but they have to do with, for instance, you have this polytope. You can take affine volumes of simplices, right? You get certain numbers, and you want to exclude those numbers, and then you want to exclude a few other numbers coming from the combinatorial situation. And if you do, then you can show that the algebra geometric side is a smooth variety, and that's basically the input we need to verify the statement. Everything else in my argument doesn't depend on characteristic.
I see. I see. Thank you, Professor.
Thanks for the questions.
Any more questions? Yeah.
Yeah, thank you for the talk. So can you say a little bit more about why the spectral sequence collapse? How do you eliminate those curves? Is it Maxwell principle or what?
Yeah. So how do we eliminate those curves? Let me just refresh my memory. The rough idea is that this divisor, this ample divisor in X, has the property that if you remove one of the components of the ample divisor, so it's a union of smooth components, right? And it has the property that if you remove one of the components, then the divisor is still ample. So it's like has some extra ampleness. And I think basically, so we have some condition in my paper with Parmigliano that says that as long as you can exclude certain certain types of curves, certain one-pointed curves. We call them one-pointed curves. Then the spectral sequence collapses. So one-pointed curves are curves in a stratum that have only one point passing through a deeper stratum. It's kind of like curves contributing to relative Gromov-Witten theory with one insertion along the divisor. So if you can exclude those, then spectral sequence collapses. We gave some geometric reason. And this extra ampleness of the divisor allows one, roughly speaking, to rule out one-pointed curves. I think our argument's a little bit more involved than that, but that's the broad brushstroke reason.
Thank you. So it boils down to maximum principle or what?
No, it has to do with not maximum principle. I think it has to do with the fact that a curve, a curve of non-zero area must intersect an ample divisor. So it's some sort of like intersection theory argument.
Oh, okay. So one
now, maybe maximum principle is a reasonable way to say it. Like if it misses the divisor, then it would have to be in the divisor complement. But then maybe exactness then says it can't exist. Right? There are no non-trivial curves in the divisor complement.
Okay, thank you.
Any more questions? So I actually have a quick question. So
sure, of course.
Yeah, as I understand, one of the consequences of your result is that in the wrapped Fourier category, an object is compact if and only if its support Lagrangian is compact.
Up to split generation. So I would say an object is compact if and only if it's equivalent to a complex of compact Lagrangians, or idempotent, completed, idempotent in a complex. That's right. But yes, that's correct. Yeah, for these large volume limits, not for every Weinstein.
Yes. Is there anything interesting to say about the quotient in this case? So mirror rule to the singularity category.
Yes, that's an interesting question. Yes, I think this is a context where so let me see if I can say this in a concise way, but there's so the singularity category, I'll just say it, I'll try to say it this way. So singularity category of x naught star is co of x naught star mod curve of x naught star. Right, so we learn that it matches the wrapped Fourier category of x naught, x minus d modulo the compact Fourier category of x minus d. But there's another way to get this, up to up to passing to opposites. There's a construction by Efimov called the categorical formal puncture neighborhood at infinity. And this is something that has some geometric significance. So there's a purely geometric way on the symplectic side involving what's called the Rabinowitz-Fourier category. I'm not sure I'm answering your question, but I'll state this and then we'll see. So work of mine with Gao and Venkatesh says that one way to access this quotient, wrapped mod compact Fourier category, is there's a direct way using some sort of Floer theory invoking this a different type of Floer theory called Rabinowitz Floer theory, which gives you the same answer. Now, if you were asking specifically, so that gives you a geometric explanation of some geometric construction of what is this quotient. On the other hand, if you're asking maybe what properties we learn about the quotient directly from the definition, I don't have as good of an answer, but I think it's a situation worth studying more.
So I was not asking anything concrete, just out of curiosity. So thank you very much.
Yeah, of course.
Okay, let's thank Sheel again.
Thanks very much.
Yep. Thank you very much. Okay, I think you now may disconnect. Thanks.
Okay. Bye.
Goodbye.